Hey everyone, I'm Manoj. Excited to join you all here. This is a conference very close to my heart. I've watched probably every PromCon talk that's already there on YouTube. I'm one of those Netflix PromCon guy, I guess. Yeah, I mean, I'm excited to very first time in PromCon, in person, in live, and also to be joining all the talking to you, sharing with you how we have been using Prometheus at scale to solve some real-world problems. Hand it over to Jorge.
Hi, I'm Jorge. I'm a principal engineer at Grafana Labs. I've been using Prometheus since around 2016 from my times at SoundCloud. Yeah, I contributed to Grafana Agent, and I've been getting more involved lately with Prometheus. Yeah.
So the topic is, I mean, you can read it all here, anomaly detection. So it's a very hotly debated topic. And if you just go back to the very founding people of Prometheus, the people who built Prometheus at SoundCloud, like people like Brand Brazil and Fabian and beyond over here, somewhere here, they have talked about it over the years. You will find blogs about it. You will find talks, PromCon talks about it, going back to 2015 and 2016. So nothing new here. The story goes like this. So we are engineers. We build code. We get alerted. And so because we are on call, and then we click a link, and we arrive at a chart like this. And now we are wondering, is this OK? Is it normal? I mean, does this metric just spikes up every day at the same time? Is it even relevant? So all those questions, and how do you then, what is the next step you do? You probably expand your time window. You go back one day. You go back to previous week. You start thinking about all the other metrics that probably are related to this and start building a story together in your head. But what if this chart looked more like this, where you already had a lot of context attached to this chart, right? So you can instantly answer a lot of the questions we were asking in the previous slide, where it could tell you, yes, it is actually above the normal, what it's supposed to be. And that's what we're going to talk about today. So a big disclaimer, like I mentioned, this has been talked a lot about it, and there's many ways to solve this problem. This is not the only way. And the reason we picked this approach is because a few desired properties or constraints, as you may call, as engineers, we always are building systems, so we want to define our constraints, and that it should work in a Prometheus-compatible storage system. It could be any one of your choice. But we at Grafana Labs happen to have a very scalable, high scalable Prometheus storage solution. It's called Mimir. You might have heard about it. So we run it ourselves. We have all our database, all our data is getting stored there. But what if you could build a system on the very highly performant metric storage you already have? And this is the last bit of space, which is very critical to all of us. It's called no magic, as in something I can explain to myself, to my coworkers, and we can believe and we can trust it, right? So that's what we are going to talk about today. How did we make a solution work with our existing Prometheus system with no magic? Over to Jorge to get started.
All right, let's build an anomaly detection system from first principles, from scratch. So you've probably seen this formula before, but this is based on the C-score. And this is typically how people get started with anomaly detection. So you want to draw these baselines that you see on the chart. And the typically way that you do that is you first have to find a middle line. Typically, it's like a moving average that follows your trend. And then you define the bands, the upper or lower bands. And you normally use the standard deviation for that and apply a factor, for example, 2 or 3. And everything that lays outside of your bands, that's considered an anomaly, right? So that's kind of like the idea where like people start. And let's see how we implement that. By the way, who here uses recording rules? All right, most people, because it's all going to be recording rules from now on. So yeah, let's start. This is the easy one, right? How do you do the moving average? Standard has this function called average over time, and we just create a recording rule with that. The main thing that we need to pick is the time window that we use. And here we decided to use a 1 hour time window because, let's see if the chart is loading. Sorry. Because there is a trade-off to make between how much your midline is lagging behind your actual metric and the smoothing factor that you apply. And 1 hour in this case, we found that is a sweet spot for that. And then we have to express the standard deviation, again, in recording rules, right? So again, Prometheus already has like a standard deviation overtime function. But in this case, we actually choose a much larger time window. Typically, you will use 24 hours. So what we want is to incorporate as much information as possible to come up with bands that actually adapt to the fluctuations in your metric. So we picked 26-hour window here because we wanted to give it a bit more headroom. Because if you have something that happens exactly every 24 hours, you might get strange patterns where your bands start contracting and they expand. Or, for example, if you have daylight time changes, and you have organic patterns, but they might actually shift a little bit. So just a bit of more headroom to get a bit more accurate predictions. Then we have to define the multiplier. We mentioned typically you can use 2 or 3. In this case, we use 2. And we just, this is, by the way, how you could express a constant in PromQL, right? You just like give it a name and give it an expression. We evaluate to 2. So this is the formula you just saw before, but expressed in a recording rule. So you take the average over time that we express with a recording rule. You take the standard deviation, and then you multiply by the multiplier. That's it, right? One interesting thing here is if you see this times on group left, basically what that means is because we're using a recording rule as to express a constant in Prometheus. Prometheus is actually, when you do the multiplication, it's going to try to match the labels on the left side with the labels on the right side. And there is no labels on the right side, so we just basically tell it ignore every label and just do the multiplication. So this is the first attempt, and it looks pretty good, right? So we have a spike. We have it moved really quickly, so it spiked up our traffic, for example. And then we see that we detected an anomaly, so it fell outside of the bands, but the bands actually expand to accommodate, to basically adapt to the trend that you're having. And so that sounds like it could work. And now we're going to talk about some of the problems that we encounter by implementing this in production. And one of them is, if I can see the graph, OK. One of them is the presence of extreme outliers. So the way the standard deviation is calculated, because it squares the differences, it can actually grow much, much faster than the average. So you might have cases where you have extreme spike and your bands will actually expand very rapidly and become very wide. And the problem with that, if you look at the arrow on the right side, is that you actually basically render your anomaly detection system useless because you stop detecting anomalies. So here's an idea we came up with on how to work around that. What we want is actually to control the speed at which the bands expand so that we find this trade-off between sensitivity and ruling out like false positives. And what you can do is actually calculate the standard deviation over a much shorter period, say 1 hour, and then you calculate that as a recording rule. And then you average that over time with a much larger time window, right? So that's kind of the smoothing function that we're talking about. And we can see that, well, that actually did what we wanted, right? So the bands now expand much slower, but actually they are now too narrow, so they are actually not adaptive enough. They lost sensitivity. So this is not really working well, right? This is not the final solution. What can happen here is that you have a lot of noise because the bands don't capture the normal fluctuations. So here's an idea, right? So let's have a look at how standard deviation works. You can see the green line actually shows like how we have spikes, down, up, and down. And you can see that every time there is a spike, the standard deviation grows, and then it goes down again, right? And when you have a stable period, you basically have a very, very low standard deviation, almost 0. So you have very low variation. And the problem is we have this watered down effect because we are looking, most of the data points that we see here are actually near 0. So we are not actually expanding the band fast enough because of this. We are focusing on the low variability periods as well as the high variability periods. So what we will actually like to do is to focus just on the high variability periods. And one way to do that is actually to apply what we call here high pass filter, but the idea is very simple. Every period that is stable, where there is not enough variability, we actually don't calculate the standard deviation. We remove these data points completely, and we just leave the high variability period. So we isolate high variability. And if we take the average over time, we'll see now how it looks. I will just show you like how you express that in PromQL because it's interesting. So we take our standard deviation over time for a 1 hour time window, and now we apply, we do a comparison. The question is, what should that threshold be? And this is a tricky question because we actually want to build a framework that works for any type of metric. And different metrics have different magnitudes, and that actually affects the threshold. So if you have a 10 requests per second metric, and you add 5 requests per second, you have a very significant change, right? It's 50% increase. But if you have a 1,000 requests per second metric, and you add 5, that's completely insignificant. That will then be considered significant. So what we need is a threshold that actually adapts to the metric that you're dealing with. And one way to do that, this is a concept from statistics called coefficient of variation. It's also called relative standard deviation. But the idea here is that your threshold that you use should depend on your metric. And one way to do that is to multiply your threshold by the average over time. So what we're saying here is every time there is a standard deviation that is higher than 50% of the average, that will be a significant change. And we will actually use that for our bands. And the final result here, you can see that this is a good compromise because the bands actually remain very stable. They expand with variability, but then they remain very stable. So they actually are much more. So this is a good compromise between sensitivity and the smoothness there. And I can show you like a comparison side by side of the 3 approaches. So the first one, you can see how the bands expand really quickly, and then we miss these anomalies. The second one actually is a bit overshooting on the other direction, and we just have bands that don't expand fast enough. And on the right side, we see bands that are stable but also adaptive. We introduce now a new problem here, right? Because we have a filter. If you have a long time window of low variability, then the filter will actually filter out everything, every data point, and then you end up with a discontinuity like that. So what you can do there is you basically introduce a new band that complements the one we just defined. And this new band will actually be purely based on the average, and its purpose is actually just to define the minimum width that we are willing to accept. So when there is a discontinuity, then what happens is basically that you will see that this band will take over, and this band will actually typically be narrower, but it will act as a minimum band. So if we combine the two, this is the upper band. We take the max of the 2 bands that we just defined, and you can see how one of them takes over the other one. We always want to look at the band that has the maximum width, so that that's how we combine them. One last problem here, right? Seasonality. So what happens when you know that something happens every day at the same time or every day of the week? You have a cron job, or people wake up on Monday every day in the morning, and the first thing they do is go to your website, and you have these kind of seasonality patterns in your data. And so actually we found a very simple but effective way of dealing with this, which is basically you apply the same formula that we saw before. In this case, we take a smaller time window for the standard deviation, just 1 hour, and we just add an offset. So we say look back one day, look back 1 week, and look at how the time series look there, and basically define bands that will adapt to what we saw before. And what it does is basically it will actually predict something that happened before, and it will expand the band before we actually detect it as an anomaly. So it's a very simple way of solving this problem, but actually we found it works really well in practice. And if we put it all together, basically now we define 3 bands. We have the margin band, the short-term band, and the seasonality or long-term band. So we do the max or the mean, depending on the band we're looking at. And this is how we combine them, right? And you can see here in this example, there are some bumps on the left side because there was like something happened 1 week or 1 day ago. And then we have a stable period, which is mostly the margin band, but when there is an anomaly, the short-term band actually takes over and expands the band. I'll pass it to Manoj to talk about the framework that we built.
Thank you, Jorge. So as you guys all see, that we have now come up with a band, which I can pretty much trust, right? Because I know exactly what happened. It's not too tight. It's not too fitting. And yet it expands when it needs to, and also knows about seasonal aspects of it, right? So now let's talk about how do I use it every day, or how are we using it every day, and how you can take it back home. So very simple, start to simple idea, a lot of recording rules you've already seen. So you got a metric. You want to decide whether it's a latency metric, and you want to take a median of that, or it's a request metric. You want to take a rate 5 minute of that because you have 30-second samples. So simply specify which is the metric you want to tag it, and with a name that you can relate with, because sometimes metric can have a very ugly name or no names at all, and what type it is, right? Because it's a request metric, or latency metric, or error metric, that helps. So with just this to a simple recording rule like that, and you also want to capture when this metric breaches a threshold, I want to record an event. I mean, in the Prometheus world, we call it alerts. But as you know, not alerts are really alerts. You don't want to wake up on them, but it's like a record event system that you can record different key breaches to your metric. So with this simple to addition, we now are able to paint everything that we showed in a Grafana dashboard. So
with back and forth.
Oh, okay. The slides. Somehow the slides are never the picture. It's a funny thing. Yeah. So you can now look at a Grafana dashboard where you can choose a metric that you picked up, and you can see the bands, and you can see the actual when it is reaching the threshold. So it's all together. Now your chart when you wake up, or you are and you want to look at a metric, it already has all the context attached to it. Now, so you can actually take it home. I mean, you can literally go tonight and try it out. Everything we talked about is in this particular GitHub repo, completely open source, recording rule, alerting rules, and you can even tune it. And we're absolutely looking to get lots of feedback. It's so easy to run. Jorge has put in the effort to containerize it, include the hotel demo app, a node exporter app, and so all the metric scraping, everything is built in, including a load generator. So you can even tune the load generator and how much traffic you want to generate. So super easy, runs on your laptop. He has been running on his laptop, from what I can tell. And so all the dashboards, you can take it and run it on your laptop. And we're absolutely looking for feedback, how exactly it's working for you and what other changes you would like to see. Now let's talk about the very first where we started, right? So what do we do now? Obviously, do we want to page people on this alert, or just log a bunch of warnings and send emails, Slack notifications? What do we do with these signals, right? That every time the metric breaches, what do we do with that alert, ALERT metric in Prometheus? So, I mean, we all know do not page in anomalies has been talked about for over 10 years now in PromCon, so we don't want to do that. We want to absolutely page ourselves only on your symptoms, symptom-based alerting. We know all about that, or SLOs, whatever you want to call it. Now, so don't go away from that. Stay with the symptom-based alerts. Now, the question is how we use it today is when the symptom-based alerts are firing, I can go back and link it back to a visual tool that shows me all the anomalies in my system. And what I'm going to share with you is how we use it inside a Grafana Cloud. So when our alerts fire, we have a link called Start Troubleshooting that takes you to a visualization that we have created here, which is going to show up soon. OK, shows up finally. So what we do is when the alert fires, we also have the ability to trace our system, so we know exactly who is talking to what. Like the alert fired on a shipping service. In this case, I've taken a fictional example, shipping service, and everything that is upstream and downstream of shipping service, called shipping connected services, here is being queried. And that's where you're able to find the ingress controller, the load balancer, and the MySQL, a database that is downstream. And all the yellow lines that bands that you see here are actually literally alert lines. So we are getting alerts from a specific API endpoint for a particular API endpoint here for latency. At the same time, the MySQL is firing anomalies on CPU and on buffer pull requests or network bytes. So again, the idea is that the errors happened, the latency breached, and system is having errors, so we got alerted. That hasn't changed. But now we can quickly link it back to all the signals which are off the charts. So with the anomaly bands, that it shows up right there. So you have a lot more context to add to your troubleshooting experience instantly. And where to signal to focus, and if there is a new deployment happen in the system or not, all that questions, you can now relate it back to specific areas where you need to focus your energy on, because your application could be fairly complicated. And that takes me to the very last slide. I want to say a quick thank you to all the people who have helped build this framework with us over the years. And if you want to chat more about it and want to start using it, join us in the community Grafana Slack channel, and we have a special new channel to talk about it with you. Thank you.
Thank you for your talk. I'm gonna try this. I'm somewhat convinced to try it on top of my SLOs. Okay. Questions? Yeah. No questions. Totally obvious. Everything was so obvious.
Yeah, hi. I wanted to know if you tried to use alt winters function in Prometheus before doing that. And also, how do you remove outliers before doing high-pass filters or stuff like that? Thank you.
Yeah, we were expecting this question because there is a function in Prometheus for hot winters, even though it's not the actual one. So there's this is the exponential moving average, right? And there is like double and triple. So the one in Prometheus doesn't incorporate seasonality. But I think, yeah, it was considered at the beginning. But first, it's more computationally expensive, and we're talking relatively large time windows. And also, it has parameters that you need to fine-tune. So if you think about what the function does at the end, right, it's basically isolating the trend from the residual, what's called, which is basically like the things that have so high variability. So it's kind of, the ideas are the same, but we wanted something that we could easily express just with PromQL that will be good enough and performant enough. So it's kind of a trade-off. So we're aware of that. We just like went down this path, but that's why we also had a disclaimer, because there is other ways, right? You can even take the data out of Prometheus and do some machine learning and all of that. So this is like a set of heuristics that we actually saw work well in practice. The second question was, sorry, I missed.
Outliers, how do you remove them
Before the high-pass filter? So, yeah, so the question is, like, how did we deal with outliers before we had the high-pass filter? So this went through a lot of fine-tuning and iteration, right? I think initially we had a much shorter time window that actually expanded the bands very quickly in the presence of outliers, because we just used the standard deviation. So we had these very wide bands that then will collapse. But eventually we settled on, we want a very large time window, so this is not acceptable, because you actually lose, the outliers will actually expand your bands too much, right? So you kind of render the framework useless. So the idea is, okay, it's basically, we added another knob that you can fine tune there. But the idea is it's useful to have bands that adapt and that loop back for a long time. But then we don't want them to distort too much the bands, right? So this is like where we try to find a compromise between that, like having yet another thing that you could tune.
Yeah, Halt Winters also has this 4-year-old ticket filed on it, which you guys can read about it. Yeah, like Jorge said, we are not sure what are the tuning parameters for across all metrics. And for latency, for example, we pick the median instead of the average. So between the average and for latency median, it works pretty well for us. And again, we are not alerting on them. These are all signals helping us.
Okay, one more question here. So thank you for the talk. There is this GitLab post, which is quite famous as well, on prediction of anomalies. And I would like to know, like, if you check this out as well, and what is the difference in the approach. From what I see, there is this part of like dealing a bit better with these like higher values or these discrepancies. But is there anything else there in your framework or in your approach that differs from what they did?
The framework is pretty much inspired by every other blog post that is out there in the Prometheus ecosystem. So again, as we called earlier, our goal was to keep it simple. That's something that works. We have running it in production and works on recording rules. Yeah, so that was our core goals. So it just builds on everything that has been there here before.
So I don't know the specifics of that blog post, but also there is a lot of literature around stock price analysis and all of these kind of things. So it borrows many ideas from different places, and it evolved over like a year or more. So, yeah.
Questions?
Thank you for the talk. I was wondering, how did you overcome overfitting? And did you have any kind of prediction based on that? Thanks.
Yeah, this is that overfitting part, right? So go back to this slide here. I think this is where the overfitting part comes in. So if you look at it, this is kind of overfitted right now, right? So once you took out, we made a standard deviation 1 hour average over 26 hours. It's kind of overfit right now. The bands are too tight. And that's where we introduced the high-pass filter. So essentially, the idea is very simple, right? Use standard deviation during the periods of high variability, because that's what you care for standard deviation. Otherwise, use a margin band. The margin band will simply tells you that above and below certain percentage, don't use it. So yeah, so high-pass filter took out all the overfitting part, made it wide enough, and the margin band filled up the gaps. So yeah, this was our solution for overfitting mostly.
The basic idea is that overfitting happens when you use too much data, right? So we remove the things that cause the overfitting, and we just remove data and then focus on just what's interesting to us, in this case, the high variability periods. So by removing data, you avoid overfitting.
Hi, thank you for the talk. I was wondering, do you have any plans to include anything like this in the Mimir, Loki, and Tempo monitoring mixins by any chance?
Yeah, we could absolutely do that. This is our first, all the dashboards, everything we showed is in open source. So we could, if this goes popular, goes viral, we can absolutely start including it in mixins. But definitely, some of the parts we are showing in Grafana Cloud, now how we use it, we are going to start using it in the Grafana Cloud and make it available to customers. And based on the feedback, we would like to take it forward.
Yeah, so it's basically recording rules and a dashboard, right? So right now, you can just copy the rules and use them. And you can add your own tagging. But if this becomes generally useful and people like it, then we might consider.
OK, one quick question.
Hey, thanks for the talk. I guess I'm just wondering, how do you know if this is working for you? How do you know that you're resolving issues more quickly? Or because you've justified it you've justified the design kind of through reasoning, but not through results.
Yeah, the goal was to find the relevant signals when the SLO alert fired. How do we know it's working? Because we are using it in our actual production, and then starting to roll it out to a few the Grafana Cloud customers here who are able to correlate all these alerting signals. We are, again, fundamentally not changing our SLO alerting approach here. But when they see it, they can quickly go back to a dashboard like this and then start correlating the signals. So the feedback has been overwhelmingly positive so far.
So I'll say it's been an experimental approach to working together with customers, and when they had issues, we adapted and fine-tuned the model. So that's how it's an experimental approach, a practical approach, more than theoretical.
OK, great. Thank you for the talk. Yeah, I learned something for sure. Thank you again.